On behalf of ISSI, it's my pleasure to welcome today, as our speaker for the Game Changer Seminar Series, Professor Roberto Maiolino from the University of Cambridge. Professor Maiolino is a professor of experimental astrophysics, honorary professor at University College London, and is a fellow of the Royal Society. But most important for the talk of today, Professor Maiolino is a worldwide expert in the formation, evolution, and transformation of galaxies and black holes across the cosmic epochs. He has used a variety of telescopes and observatories, and now is very busy dealing with the fantastic data from the James Webb Space Telescope. And today he will speak us about these amazing results that he's getting from this extraordinary telescope. Before I give the floor to Professor Maiolino, for those of you who have just joined, if you have any questions for our distinguished speakers, please put them in the chat. And at the end of the seminar, I will go through the questions and ask one question each by each. So just hold on to your question, put them in the chat, and Professor Maiolino will answer them. You have the floor. Welcome.
Thank you, Antonella. Thank you for the kind introduction. And hello, everyone, and thanks for joining. So during this presentation, I will try to briefly summarize some of the intriguing results that we are obtaining about the early generations of black holes in the early universe, as found with data from the James Webb Space Telescope. Just let me start to introduce the topic. We know that most, if not all, galaxies in the local universe host at their center a supermassive black hole, and by supermassive we mean with masses ranging from a few millions to actually a few billions of solar masses, and including our own Milky Way. And this was first found by tracing the motions of the orbits of the stars, in the proper motion of stars in the center of the galaxy, and finding that they orbit a very massive objects, actually invisible in most wavelengths. And this was then, and actually this was resulted in, as you may know, in the Nobel Prize a few years ago. And then this was also the shadow of the black hole in the center of our Milky Way was also imaged by the Event Horizon telescope. However, in the black hole in our galaxy is a peculiar case. In most of the galaxy, we infer evidence for the presence of central supermassive black holes with other techniques. And this is actually an outdated summary of the black hole masses measured dynamically in several other nearby galaxies. And the interesting thing is that they seem to have the black hole masses correlate with the properties of the host galaxy. For instance, in this case, with the mass of the spheroidal component of the galaxy, and finding that essentially the black hole masses are typically 0.1 to 0.5% of the mass in the host galaxy, depending on how you measure it. And also will be relevant for what we'll discuss, there is an even tighter relation between black hole mass and the velocity dispersion of stars in the central region, which is therefore more linked to the dynamical properties evolution of the central region of the galaxy, and of course also the dynamical mass in the central region. Now, however, in the vast majority of cases, especially in distant galaxies, black holes are identified only when they are active in their accretion phases, and we see them through the bright emission from coming from the accretion disks, and also from the surrounding gas, which is illuminated and ionized by the radiation from the accretion disk, which is typically, this gas is characterized by very high densities, very high motions around black holes, and very high ionization. And in these phases, these black holes are called active galactic nuclei, or AGNs. And when they are very luminous, also quasars or quasi-stellar objects. And in these cases, they can totally outshine the light from the stars in their host galaxies. And now, how these supermassive black holes came to be? I mean, standard scenario is that they could have started from the remnant of massive stars, which collapse into form black holes from a few times of the order of a few times the mass of the sun, up to potentially even a few hundreds, according to some models. Then they accrete matter from the surroundings, and they grow to become very massive black holes. One issue is, however, that they can't accrete at whatever rate they want. There is a limit, which is called the Eddington limit on the accretion, which is given by the requirement that the light emitted by the accretion disks exerts a pressure, additional pressure on the surrounding matter. And when this pressure is stronger than the gravitational pull, then at that point the black hole sort of suicides, because it's essentially expelling the gas out of which it's feeding from. And so this limit actually is not so tight, in the sense that there are models which envisage that the black holes can actually undergo short bursts of super-Eddington accretion, and there are also models where self-shielding along the disk can also potentially allow super-Eddington accretion. Another channel for growth is merging with other black holes, and this we know that is very likely happening. Although it's based on various arguments, it seems that the bulk of the accretion seems to happen through gas accretion. Now, how do we explore these scenarios? Well, we have to look back in time when the stars and galaxies formed, and when black holes formed and grew. And looking back in time means looking at very distant objects, because, of course, because of the finite speed of light, the farther we see these objects, the farther we look back in time, because we see these objects not how they are now, but as they were when the light started traveling towards us, that is, in many of these cases, billions of years ago. The additional issue is that because of the expansion of the universe, as light travels toward us, it is being stretched in wavelengths, which means that this light becomes redder and redder and goes into the infrared. So to explore these scenarios, we have to look at very distant objects, so very faint, and so we need a lot of sensitivity. And we need to look into the infrared because of the cosmological redshift. And for this, the James Webb Space Telescope is the perfect machine, because it is the largest telescope in space, has a fantastic sensitivity, unparalleled by any other facility, and also it's optimized for observations in the infrared. And this is clear from this graph, which shows the sensitivity of the various instruments on board of James Webb compared with the functional wavelength, compared with ground-based facilities and previous space missions. And you see that in some bands, the improvement in sensitivity is of even 3 orders of magnitude, which is gigantic. I mean, this kind of improvement really rarely happened in astronomy, and even more broadly in science. Just putting into a context, this is essentially equivalent in the visible to instantaneously upgrading Galileo's telescope to modern large telescopes. So you can imagine what is the discovery space that Webb has opened. And indeed, Webb hasn't disappointed. Just to put this into broader context, let me mention that black holes, very massive and actually hypermassive black holes with masses of billions of masses, even before James Webb in the past 10, 20 years, were discovered also in the up to when the universe was only about a billion years old. And this is shown here in this diagram where you see the location of the masses of these black holes. And these tracks here show in this diagram where you have on the upper axis the age of the universe, and on the bottom axis the redshift, is the amount of wavelength shift that is actually the direct measurement that we make, that we have. How these black holes would have evolved in the previous cosmic epochs if they had accreted at the constantly at the Eddington limit. Okay, and you see that it is already something very challenging to explain, because they even they should have formed essentially in the first few tens million years after Big Bang, and even in that case with seeds which are very massive, more massive than what you would expect from simple stellar remnants. So to explore and understand what might be the origin of these hypermassive black holes, Webb is a fantastic machine, because it allows us to investigate even lower black hole masses and higher redshift, and therefore investigate how these black holes may have formed in the earlier universe. And this illustrates how indeed Webb has been highly effective in opening a completely new discovery space. So this is the luminosity of accreting black holes, AGNs, as a function of age of the universe or redshift. And you see in the crosses and these gray contours illustrates what was known, the kind of AGNs and quasars that were known before Webb. And this solid symbol instead shows the several dozens of AGNs that have been discovered by Webb, which are indeed much fainter, much lower luminosity, sorry, than the previously discovered black holes. And this could be either because the black holes of these new AGNs are smaller, or because they are accreting at a lower rate, and also pushing to higher redshifts. And this is to illustrate one of these AGNs or accreting black holes that has been identified. So the image is not very, how to say, intriguing. It's just essentially points to what this halo that you see here is mostly the PSF of the telescope. What is most of these black holes, AGNs, were identified primarily via spectroscopy. And the spectroscopic properties of these AGNs obtained with the Webb are fantastic. We obtained spectra which have extremely high signal to noise, and to the point that in cases like this one, we have to plot the flux in logarithmic scale to see what is the level of the noise. Some of these lines have signal to noise up to 1,000, which is fantastic. It's sometimes difficult to obtain even for local galaxies. And how do we identify that this is an AGN in a accreting black hole? Well, the transitions of hydrogen and helium have these extremely broad components, which are essentially typical of the very dense gas orbiting around very fast around the black hole, which is the so-called Broadband region. But we also see these other highly ionized transitions, much narrower, which comes from the so-called northern region, which is highly excited and highly ionized by the energetic radiation field emitted by the accretion disk around the AGN. In this specific case, we can use these broad components of these lines to infer the black hole mass, in this case is about 10 to the 8 solar masses. But we have now several of these measurements, which are summarized in this diagram. And so here you have the accretion rate relative to the Eddington limit as a function of black hole mass. And here in these orange points, you see the previous measurements from quasars at high redshift that were measured with previous sensitivities. And these blue symbols instead illustrates the black holes and AGNs discovered with Webb. And you see that they essentially, as expected, we are probing now black holes with much lower masses than the high redshift quasars, and with a broad range of accretion rate from relatively dormant black holes all the way to black holes potentially accreting at even super Eddington rates. And these blue stars here is the most distant AGN or black holes found so far, which is indeed found to accrete well above the Eddington limit when the universe was about 440 million years. And this is this most distant black hole is JWST, which was published recently on Nature. And again, in terms of imaging, it doesn't look anything spectacular. It's just merely a point source with some emission around it associated with its host galaxy. But again, we identified that this is an accreting black hole thanks to spectroscopy. In particular, in the ultraviolet flame, we have diagnostics that of the gas density in the nuclear region of this galaxy, which indicates that the density of this gas are extremely high, totally inconsistent with the densities of the standard ISM, and instead fully consistent with the high density found in the Broadland region around supermassive black holes. We also find extremely powerful winds, which with the velocity which are very high, again difficult to explain with normal star formation scenarios, but well common in winds driven by AGNs. We also find ionized species, which are also typically found in the surrounding of accreting black holes, and also ionized gas with sort of ionization core-like structures typical of AGNs, and also a really giant Lyman alpha halo, which is typically, fully consistent with the same kind of giant halo seen in high redshift AGN and quasars. So the mass that we infer from this black hole is about 2 million solar masses, and as you see, can easily be a progenitor of one of the hypermassive black holes which have been identified in later epochs. So with Webb, we have moved this problem of understanding this the nature of these black holes to earlier cosmic epochs and lower masses. The other properties that I mentioned, this black hole seems to be accreting at a rate higher than the Eddington rate, and is interesting, is also being found in other cases more recently in even a more direct way through actually direct measurements of the Broadland region at lower redshifts. And the other interesting aspect is that if you try to explain this black hole with an Eddington limited accretion, you see again you run in this problem that you struggle to explain it with standard stellar remnant seeds, because you would have to go at extremely early epochs to explain it with a simple stellar remnants accreting at the Eddington limit. So there have been various theories which have been proposed in the past to explain this the growth of these supermassive black holes at high redshift, already in place at high redshift. One of these is the so-called direct collapse black hole scenario, or heavy seeds. In this scenario, you have a pristine, massive pristine clouds of gas, so made only of hydrogen and helium, which are photobly dissociated, so there is by external UV radiation, so the molecular hydrogen is dissociated in atomic hydrogen, and these essentially prevent the cloud to cool properly and avoid fragmentations. And as a result, this cloud can collapse directly into a very massive black hole, possibly passing through intermediate brief stage of massive protostar. Then when you have a black hole which has a mass so high, then it takes very little to grow to supermassive black hole sizes with some accretion. So in that case, essentially, the scenario to explain these very massive black holes at high redshift is that essentially they are born big, and so that solves most of the problems. The other scenario is that there are very dense clusters of black holes and stars in the center of galaxies, and this results into a very rapid runaway merging, and which produce an intermediate mass black hole. And also in this case, with accretion, you can explain these supermassive black holes at high redshift. The other scenario is that still the seeds are actually remnants of massive stars, possibly the first generation of stars that are the so-called population tree stars from the pristine clouds. So the seeds are actually very small, but there have been accreting at the super Eddington rate. And most models expect that super Eddington accretion is not really possible as a steady mode, but it's many models do expect that you can have short bursts of super Eddington accretion. And these short bursts, essentially, of course, tend to expel, inject a lot of energy in the interstellar medium, so they actually probably expel most of the gas out of the galaxy. But the short super Eddington phase is effective enough in allowing these black holes to accrete significantly and become possibly these supermassive black hole. There is a fourth scenario that I don't have time to discuss, which is that actually the first seeds were formed during the Big Bang, in particular in the inflationary phase. These are the so-called primordial black holes, and this is a fascinating and intriguing scenario, more difficult to test, but is yet another possibility. So these various scenarios essentially, so heavy seeds, so black holes born big, intermediate mass seeds, or light seeds accreting with bursts of super Eddington accretion. These, you see them overplotted here. They can all explain equally well the black holes seen in GENS 11. So we are still degenerate trying to explain the origin of these very massive black holes in the universe. So we need additional information. And potentially this additional information comes from comparing with other properties of these of their host galaxies. This is the black hole versus stellar mass relation of these AGNs, black holes found by Webb or characterized by Webb. And you see these compared with the local relation that I showed a few minutes ago. And the characteristic of most of these is that they are significantly overmassive relative to the local relation. So while in the case of local black holes, they are just 0.1 to 0.5%, a small fraction of the entire mass of the host galaxy. For some of these high redshift distant black holes, they can have masses which are approaching the mass of their entire host galaxy. Okay, so of course here there are a lot of selection effects in place because we, of course, struggle to find even smaller black holes. But even the bare existence of such overmassive black holes is very intriguing because it's telling us something about that. It's telling that nature is somehow managed to create these monsters living in relatively low mass galaxies. So, as you may have known, JWST has revealed that early galaxies grow very fast, faster than we expected. Well, early black holes grow even faster, apparently. Now, here I try to summarize what two of the graphs, key plots that I've shown previously. So, Eddington accretion rate versus black hole mass, and black hole mass versus stellar mass. And now I would like to focus the attention on this specific black hole, which is particularly interesting because it is accreting at a very low rate, so about nearly 2 orders of magnitude below the Eddington limit. So essentially is what we could call a dormant black hole. But it has a mass that is about as high as the mass of the distant black hole found in distant quasars. But being so underluminous, it allows us to explore and understand its host galaxy much better because it's not outshining the host galaxy as in the case of quasars. And the host galaxy turns out to be quite small. And as you can see, the black hole is nearly as massive as the host galaxy. And this is quite intriguing because if you compare with models and simulations, logical simulations in some of these scenarios, this can be differentiated between some of these models. So what you see here is this, now focusing again on this specific black hole. These, in gray, you see the predictions of heavy black hole seeds, so direct collapse black holes, accreting at the Eddington limited. Okay, so accretion is limited to the Eddington value. And you see that in this case, these black holes struggle to produce such high black hole to stellar mass ratio, but also they struggle to produce such low Eddington ratios at high black hole masses. The reason is that in order for this model to produce such massive black holes at being capped at the Eddington limit, they have essentially to nearly constantly accrete close to the Eddington limit. Otherwise, they don't manage to produce these very massive black holes. Instead, what you see here in red contours are models where you can have light or heavy seeds, but experiencing short bars of super Eddington accretion. And so in this case, you see that these bars, even if these bars are very short, they manage to produce very massive black holes and also to reproduce the black hole to stellar mass ratio observed in these objects. And also the very low accretion rate seen in this object. It may sound, may appear counterintuitive that to explain a dormant black hole, you have to invoke a super Eddington accretion scenario. But it's not so weird because essentially what's happening is that in this scenario, black holes experience very short bars of super Eddington accretion, which enables them to grow very quickly in those short bars. But then the black hole can be dormant for very long periods, and so it's most likely to find these black holes being dormant in this scenario than in the short active phase, and this is shown in these contours. And also, of course, the problem is that finding these dormant black holes, even with Webb, is very difficult because they are very faint. They are essentially barely visible. But you can see that this is probably just the tip of the iceberg of a vast population of dormant black holes that are below the detection limit, even for Webb. So it's just the tip of an iceberg. So interestingly, these properties of being overmassive is only relative to the stellar mass of the host galaxy. When compared with the velocity dispersion, and we can do that with Webb, these black holes seems much more aligned with the local relation. And so this relation, the black hole sigma relation, was already indicated as being more fundamental than other relations because tighter. Well, these results from Webb is indicating that this relation is not only more fundamental, but probably more universal in the sense that it remains more or less constant across the cosmic epochs all the way to the first few hundred years, in the million years, sorry, in the universe. And so since the velocity dispersion is essentially telling us information about the total dynamical mass in these galaxies, the fact that the black hole sigma relation is aligned with the local one is telling us that probably the baryons are mostly there and about in the right amount, but so the gas is there, but somehow stars failed to form as efficiently as black holes. So probably the black hole's growth through accretion has suppressed the formation of stars without removing actual gas, probably through a negative feedback in terms of photodissociation and heating of the gas, which has prevented the gas to collapse efficiently to form stars. Let me conclude in the last few minutes by mentioning another channel of potential growth that I hinted at in the first part of this presentation, that is the potential role of merging. So we know that galaxies can merge. This is a relatively, how to say, rare phenomenon in the local universe, but we know that is much more common in the early universe. And of course, when galaxies merge, there is the possibility or the expectation that the black holes at their merger and their centers can merge as well. And we now can explore this scenario with Webb. And one additional intriguing finding has been that the finding of with Webb of a large number of dual AGNs at high redshift in the early universe. These are just a few examples, but we are finding that dual AGNs, that is pairs of galaxies hosting and accreting black holes with separations of a few to several kiloparsecs, are quite common. About 20 to 30% of AGNs are in dual AGNs. And this is much higher than what was expected by models and cosmological simulations, but higher by an order of magnitude. So it's telling us that probably there is something is an important feature of black holes and accreting black holes at high redshift. The question is, however, these are still very large separations, so far from being, how to say, potential black hole mergers. So the question is whether these black holes actually eventually merge. And this is a fair question because there are a number of simulations that expect that when the galaxies merge, actually black holes may not merge with them because black holes may behave like stones in the air, so that essentially are not slowed down by the dynamical friction of their stellar component. And so while the galaxies merge, the sinking time of the black holes is far longer, possibly even longer than the Hubble time. And so this results in black holes which are left wandering in the halos of these galaxies. So it's not so obvious that galaxy merging resulting to black hole merging, and therefore that contribute to the growth of black holes. However, with Webb again, we are finding increasing indications or evidence for pairs of black holes with much smaller scales of a few hundred parsecs, so within the size of a galaxy, even in these early galaxies, these early times galaxies and smalls, and we are finding that black holes can be actually in pairs on such small scales. And the first indication came from the finding that these broad components of the some of these hydrogen lines have a quite peculiar structure that can be well reproduced by assuming that actually they are coming from two broad line regions, so two components of dense gas orbiting two separate black holes, and this is one of these cases. However, even more interestingly, we are finding now even, I mean, at the limit of the spatial resolution of Webb, we are finding cases in which the black hole is actually spatial, with spatially resolved spectroscopy. You can find cases in which black holes with their broadline region are not only offset in velocity, but also spatially offset from the center of the host galaxy or in a galaxy with which it's going to merge, and providing additional evidence that these black hole merging or black hole pairs on scales on a few hundred parsecs is actually happening with these early epochs, so within the first billion years after Big Bang. And with the new data that we have, we are finding more and more examples of these cases. And this is indicating that black hole merging can be actually an additional important channel for a rapid growth of black holes in the early universe. And in this case, keep in mind that I'm not talking about the merging within the central dense cluster of stellar-like black holes. I'm talking about merging between supermassive black holes. And this merging of black holes is, of course, in the early universe is expected to produce gravitational waves, and these will be detectable with future gravitational waves missions such as LISA, which has been recently approved by the European Space Agency. And in this sense, Webb is paving the way to LISA by finding statistics on how many black holes we are expecting to find in the merging phase in the early universe with these observations. And I would conclude here by saying that Webb has revealed that not only in the area of black holes, but more broadly, that the early universe is much more dynamic and active than we were expecting, honestly. It's full of surprises. And this is just the beginning, because this is just the first 1.5 years of observations. I'm sure that the most exciting discoveries are still to come. And thank you for listening.
Thank you, Roberto, for this fascinating talk. It's wonderful to see how 1 year of JWST observations are starting to shape this field. So it's really fascinating. As you can see, a lot of interest from your comments, because we have a very lively chat and a lot of people waiting to ask questions. So I will proceed with the first question from Andreas. Is there an estimate to what proportion supermassive black holes are due to merging black holes compared to gas accretion?
Right, this is exactly the question that we are trying to assess. We have now a new large program with Webb, which has just been accepted in cycle 3, which is indeed, one of the goals is indeed to assess this fraction. I can't honestly give a quantitative answer now, but is one of the goals in the coming years, specifically with this new large program. Yeah.
Okay, thank you. So we have another question by Bozina Cerny saying, how efficient is the cooling of the pristine cloud? It has low metallicity.
Yes, indeed. It's very inefficient, and that's why it's thought. I mean, if it's thought to be, if you're talking about the pristine cloud that is forming putative black holes, the light black holes, is very inefficient, because in that case, the models are assuming that it's being irradiated by the stellar UV radiation fields with photodissociated molecular hydrogen, and this makes the cooling even more inefficient. And that's what is needed to avoid fragmentation of the cloud, and therefore allowing the collapse of the cloud directly into a massive black hole. I must say, however, if I may, this scenario of direct collapse black holes with these, how to say, poor cooling in the cloud, with this, how to say, specific circumstances where the cloud is irradiated by an external strong radiation UV fields, were, how to say, posed when, how to say, the scenario of having superhélice accretion was essentially not taken seriously, if I may. But now that we see that there are cases of superhélice accretion, I think the need for this specific channel is which can still be there, but whether that's is a dominant channel for the formation of the early black holes maybe has to be revisited.
Thank you. So one comment to people who joined, if you have any questions, please do not raise your hand, but write your question in the chat, and I'm just going down the list and I will read them one by one. So please write your question in the chat. So there is another question by Isaac Smith, who says, couldn't be there some combination of heavy seeds that collapse non-uniformly to make nuclear cluster, but all of this is hidden in a direct collapse? Essentially, the cluster formed during direct collapse, so that everything ends up with one large black hole?
Yeah, no, this is a very possible scenario. I have oversimplified the scenario in 3 big categories, but I think there are hundreds, if not more, papers suggesting different growth scenarios, which are can be incorporated in one of these categories or a variant of this category. And I think I do remember that there is one or a couple of models even that indeed expect exactly this scenario. It is a sort of pre-fragmentation in smaller black holes and then a subsequent merging. So it's two-step process. Absolutely is a possibility. Yeah.
Thank you. We have a comment by Professor Norma Sanchez, who says, good data, but interpretation problems. The growth of supermassive black hole scenario do not work. The point is that they not include an ingredient of galaxies and of black holes, which is dark matter. Do you have any comments? And did you have an answer?
No, well, no, there is, in many of these are actually embedded in full cosmological simulation, which have the full ingredient of dark matter. So I would say that essentially nearly all of these models, the hundreds of papers that I mentioned, do actually include the dark matter component, and that indeed plays a role. Actually, I may actually even expand on this, that in this scenario of primordial black holes, which I haven't discussed much, but in that case, the primordial black holes have even been proposed as being a possible significant component, if not in some case models, dominant components of dark matter. So in that case, it's a sort of self-consistent treatment, but I mean the interpretation of dark matter in terms of primordial black holes, I think, goes well beyond what we are discussing here.
Thank you, Roberto. Michela Mappelli is asking, how short is a short burst of super Eddington accretion?
It's the order of 1 to 2 million years, something like that. It depends on the model. There are different models. And these it cannot be much longer than a few million years, because the radiation pressure in these short bars is so strong that essentially expel most of the gas in the galaxy, and so kills both star formation and further accretion. So this is, I think, consistently seen in most of these super Eddington scenarios.
Okay, thank you. And related still to short burst accretion, Isaac Smith is asking, for short burst accretion, what could this material be? Instead of an accretion disk, could it be large stars that are directly accreted?
Yeah, in potentially the problem of the gas is much easier to accrete because it has viscosity, and so it's easy to accrete into black holes. Large stars are essentially behave like how to say stones, which have only dynamical interaction with the black holes and the rest of the galaxy. But there are so it's more difficult to make them accrete them unless, as some models indeed expect, and it's yet another possibility, they are tidally disrupted. In that case, they can essentially, yes, provide the material for accretion.
Thank you. We have a question from Nuno Pereira asking, could the origin from the supermassive black hole formation be overdense regions of dark matter that cause huge clouds to collapse into a singularity?
This is exactly the scenario of the primordial black holes. I think the most recent models in this case is indeed that in some of these regions, some fraction of the dark matter is actually made of clusters of primordial black holes, which, according to these recent models, the primordial black holes have strong clustering. So they have large concentration in some region of overdense of density of the universe, and these clusters of primordial black holes can actually emerge to form these more massive black holes. So yes, it's a possibility.
Thank you. So I have to tell you that the chat is growing by the minute. So we'll give it another 10 minutes and see where we end up. But a lot of interest for your talk, Roberto. So Bozina Cerny is asking, what forces the vigorous star formation just before you start feeding the black hole? You need the star formation rate to produce all those heavy elements in spectra look quite normal, similar to nearby AGNs.
Yes, well, I'm not sure I understand the question, but well, there are two things, however. The star formation, I mean, the mass that we're talking about in this AGNs is in these galaxies is relatively small. It doesn't take much to enrich to even 10% of solar in very quickly. And this is predicted by most models, and this is what we find when analyzing the metallicity of these galaxies out redshift of 10. We find that most of them are already, despite the early epochs, are already reached very quickly to 1/10 of solar. So the enrichment is very very quick, and it takes very little. I mean, if one takes a simple chemical evolution model to close box, it's essentially it takes a few tens of million years. And of course, if you have accretion, this dilutes the metallicity, and one has to incorporate that more carefully. But it's not something that particularly demanding, I would say. Having said that, it's true that I wouldn't say that these most of these have normal chemical enrichments, because especially at such high redshift, such as in the case of GNZ11, we are seeing that the chemical abundances are actually not quite anomalous. We don't tend to see them in lower redshift galaxies, and indeed there are a lot of studies that invoke the first enrichment from the first generation of stars in terms of very massive stars or early Wolf-Rayet and early AGB for pollution. So it is indicating that we are indeed witnessing an early phase of the formation of these galaxies, also from the chemical perspective.
We have now a question of Erika Melli, who is asking, using relations calibrated at redshift 0 to retrieve black hole masses at z = 6, couldn't this be a source of uncertainty and potentially overestimated massy and or bolometric luminosities?
Yes, absolutely. This is a question that we keep asking ourselves, and is a very good point. Let's say it has been very intriguing. For instance, a recent result from the gravity team. Gravity is an instrument, interferometric instrument at the Very Large Telescope, where they managed to measure directly the black hole mass in distant black holes at redshift 2.5, so lower than this, but still very high redshift. And there they could measure directly the black hole mass and comparing with what we estimate by using virial relations. And okay, they find that we're using some diagnostics which the black hole mass is off by even an order of magnitude or more. But when using H alpha, which is the one that we use with the Webb in most of these galaxies, the difference is only a factor of 2.5. So it seems that the local, and even this difference, is probably due to the fact that this specific black hole is accreting at high superheading. So there is a reason for that. So anyway, the difference is very small compared with the huge difference that we are seeing on the scaling relation. That is the overmassive nature of these black holes being 100 or 1,000 times above the local relation cannot be explained even if we incorporate this factor of 2 or 2.5. So I think we are reasonably confident that, of course, the local relation have caveats in being applied at high redshift, but we probably are not far off.
Thank you. So Luis Vega is asking, related to the sigma mass plot, are the first AGN virialized? If not, sigma will not be related to mass.
Yeah, it's well, I'm not in that plot. I'm not how to say, connecting directly to mass. I'm just showing that the velocity dispersion relation is close to the local one, and that at that point is just, how to say, an experimental finding without any interpretation. Then it may be a coincidence that they have completely different physics and they are aligned in the local relation, or can be actually tracing the same thing, that is the dynamical mass is not much different. Let's say in the cases of the few cases where we can measure the directly the stellar velocity dispersion, not through the gas, we are finding consistent results. So this gives us confidence that we are essentially obtaining a relation similar to that in the local universe. Additionally, in many of these cases, sorry, the profile, we have integral field spectroscopy, so we can study the profile, the spectral and spatial profile of these lines, and we don't find strong evidence for significant outflows or inflows that may deviate strongly from how to say, may affect significantly the width and velocity dispersion of these lines.
Thank you. So Hans Zinnecker, hello Hans, is asking, could it be that in the heavy seed scenario, when pristine cloud collapse, a supermassive binary black hole might form? Any collapse involves some rotation, and hence perhaps fragmentation into a least two orbiting object.
Yes, it's very possible. As I mentioned, I think there are indeed models which envisage an intermediate stage where you form not a single black hole, but 2 or 3 or more intermediate mass black holes which then merge later on is absolutely plausible. I think the single black holes is probably an extreme case, but whether you form a single one or a few which then merge, in the end, it's fine, doesn't change the main result. That is, in the end, you manage to form in this with this channel relatively very massive black holes already very early in the universe, which is then easy for them to make supermassive black holes at these early epochs. That's the main point, I think.
Okay. So you have a thank you message from Brian McNamara. And you have another question from Charles Horowitz, who is asking, what are the implications for the next generation ground-based gravitational wave detectors?
Yeah. We exactly one of the motivations of the JWST large program that we just got approved was just this, to assess better the rate of these black hole merging and the black hole mass ratios, and so to provide better predictions for LISA in particular. And indeed, one of the figures in our proposal was indeed that I don't know if you're familiar, but it was the waterfall LISA sensitivity chart, and showing that we can actually probe the high redshift part of these predictions, and therefore provide the expectation for LISA, and therefore for the observing strategy, the possible design, and so on. So what are the implications? I can't yet tell now, because maybe we have another seminar in 1 year from now when the large program is finished, but we should be able to provide some constraints. Yeah.
So we have a question from DBA Charing asking, do the massive black holes only exist at the center of galaxies?
There are locally, there are also claims of supermassive black holes which are off-center or off-nuclear, possibly ejected as a consequence of these merging events. And some of them disputed and so on. And also this finding that we are obtaining at high redshift, for instance, with Webb or offset black holes, could also, we discussed this in the paper, could also indeed result from as a consequence of emerging, which results into a kick, a gravitational kick of the resulting black holes, which gets offset from the center of the galaxy. So these are all possible scenarios. So it's very possible, yes, there is some observational evidence. And even in the case of the displaced black hole, because it received a gravitational wave kick, is still indicating that a black hole merging happened. So in one case, we are, as to say, saying that a black hole merging is about to happen. In the other cases, we are saying that the interpretation is that it just happened. Having said that, in most local galaxies in which we could trace the black hole, the central black hole dynamically, or even through accretion, the black hole is consistent to be located essentially in the center of the galaxy.
Thank you, Roberto. We have really time for only a couple of more questions. This is the liveliest chat I've ever seen. So congratulations for generating all this interest. Chris Dunn is asking, have you done a comparison of the low mass superacting AGN at IZ with their counterpart in the local universe, which are in the narrow line Sievert run?
I mean, as of today, I'm writing a paper on that, and indeed, it's an exciting topic. I don't want to spoil the paper, which hopefully will be posted in the coming few weeks. But we are indeed investigating that in terms especially of X-ray emission and properties of the circumnuclear gas. And it's intriguing. It's essentially are probably siblings of what we see in local naturalized ones. But I am glad to provide you a draft as soon as it's ready, hopefully in the coming few days.
Fantastic. And I will choose one last question. Nicholas Rory, do you think that 100 million years for the start of stars and 200 million years for the start of galaxies are the right values based on contemporary data? Also, do you think the most appropriate time for start of black holes creation?
Well, there are models and simulations that do start. I mean, it depends what start means, because it's not that it's a sudden sharp event in the universe where suddenly all stars appears and galaxies form. So it's essentially been a growth, gradual growth. So certainly there are simulations and models where first stars start already forming in the especially for the model for the 21 centimeter signal, where the first objects start forming yes, as early as 100 million years after Big Bang, and galaxies get how to say assembled yes, in 200 or 300 million years after Big Bang. We have some interesting new results from our programs in this context that again will be published in hopefully the next month, and which are providing new insights on this. I can't now expand much on this, but we're making a lot of progress. Yeah.
Thank you, Roberto. We look forward reading all your future papers, and thank you so much again for this wonderful talk and the patience to answer the million questions that our viewers had. So thank you again, and thank you to all of you who tuned in for these very exciting results. And stay tuned, more developments on this field coming very soon. Thank you.
Thank you. Thank you, everyone.
Thank you.
Thank you,
Thank you.